in the UK, and we are about 3/7 in Malaysia now. All right, welcome to our international webinar on Magic pilot projects. To be specific, our international webinar title today is on developments of marine material joining innovation inspection system for underwater ship hulls and marine structure. Before I proceed on, I would like to read to you the agenda for today, for the webinar today. All right, so at the beginning, so I will do the openings and also do some introductions on the needs and benefit of MAGICS, introduction about UniKL MIMET, my university, TWI UK, and also I will introduce the speaker and also the moderator. Then it will be followed by Mr. Jonathan to talk about the background of TWI and NDT section under MAGICS overview. And then we will start the presentation by Mrs. Lu Zhao. He will speak on the inspection systems, phase array ultrasounds, well follower, data analysis, and thereon. And after the presentation by Mrs. Lu, there will be a short video about the equipment. It's about 2 minutes or so. And then will be followed by another about 5 minutes by my colleagues, Mr. Zamari. He will talk about introduction of URSB Marines, and then I'll speak a bit on how this question and answer will be carried out in this webinar. All right, ladies and gentlemen, the needs and benefit of MAGIC inspection system. So, as you can see from the screens, so that is the equipment we are talking about. All right, so it's an inspection system developed by TWI UK under MAGICS in collaboration with University Kuala Lumpur through the commercial arm of URSB and also UniKL MIMET. All right. So this particular equipment inspection system is used for underwater inspection of ships, hulls, and marine structure. As you are aware, the current techniques of underwater inspection are mainly by visual observation and touching. No volumetric flows techniques as yet, not until very recently. So the pilot project for Malaysia by Material Joining Innovation Center or MAGICS or TWI, it is a project of a consortium between TWI MAGICS, UniKL Commercial Arm, URSB, and UniKL MIMET. This project is funded by our stakeholder MARA through URSB and UniKL MIMET, and the budget allocated was about 4 million ringgit Malaysia, and it is supposed to be the first automated underwater phase array inspection system. So if I can summarize the technical specification on this equipment, all right, the MAGIC equipment navigates on the ships of a hull via remote controls, capable of inspecting ship hulls with a thickness range of 8 to 20 millimeter, and it will be able to operate up to 20 meter underwater. Of course, this is the pilot project. For the future, we can upgrade it to a deeper depth of water. And it will find and follow the well using guidance system, provide full well volume inspection using an advanced encoded phase array techniques. It will track the path of the vehicle while it is traveling underwater, offer offline data analysis capability, and the data collected can be analyzed using dedicated software. All right, to proceed on, I would like to introduce a little bit about my university, UniKL MIMET. In full is UC Kuala Lumpur, Malaysian Institute of Marine Engineering Technology, as we are members of the consortium in developing of these MAGIC equipments. So that is the aerial view of UniKL MIMET. And we are one of the 12 institutes of University of Kuala Lumpur. We are located in Lumut, small town of Lumut in the state of Perak, about 250 kilometers north of Kuala Lumpur. It is a marine campus dedicated for marine engineering technology programs, and we offer complete level of study from diploma, bachelor degree, master and PhD degrees in maritime technology and maritime management. All right, so we have 4 diploma programs currently running. They are ship design, ship construction and maintenance, marine engineering, and electrical electronics marine, bracket marine. All right, so we have 4 bachelor degree programs. As you can see there, it is a Bachelor of Engineering Technology, Naval Architecture and Shipbuildings with honors, Electrical and Electronics Engineering Technology, Marine, and we have a Marine Engineering Technology with honors for Marine Engineering, and we have also Bachelor of Engineering Technology Offshore with honors and Bachelor of Maritime Operation with honors. All right. We also offer postgraduate programs. So at this moment, we have Doctor of Philosophy in Maritimes, Master of Engineering Technology in Maritimes, and Master of Maritime Operation and Management. The Marine campus currently houses about 1,100 students, part of the overall population of more than 20,000 students at the university. And it is very unique because we have a shipyard within the campus. And our future program we are planning now is Diploma in Maritime Operation and Bachelor in Technology in Coastal and Subsea Engineering. Good. Allow me to talk a little bit about TWI UK. So that is a picture of the aerial view of TWI United Kingdom, the headquarters in Cambridge. TWI was established in Cambridge in 1946. It is a member-based organization supporting both individual and companies alike. Exists to provide authoritative and impartial expert advice, know-how, and safety assurance through engineering, material, and joining technologies. TWI descended from British Welding Research Association, BWRA, and it is the foremost independent research and technology organization in the world. It spans innovation, knowledge transfer, problem resolution across all aspects of welding, joining, surface engineering, inspection, and whole life integrity management. TWI has over 800 consultants, scientists, engineers, and support staff. And at this moment, they have more than 1,800 industrial member companies in over 70 countries, 5 in the UK, and 13 overseas facilities, including 1 in Malaysia. That is Southeast Asia TWI. So the Cambridge-based headquarters operate from 54,000 square meters of manufacturing, testing, training spaces, and various more. So the innovation network undertaking joint research program and developing next generation of engineers and scientists. TWI is actually a professional institution, and they have a separate membership of more than 6,000 individuals. Ladies and gentlemen, I would like now to introduce the speaker and also the moderator of this webinar. The speaker is, of course, Mrs. Lu Zhao. She is from TWI. She joined TWI in 2009 after obtaining her Master of Engineering and Bachelor degree in Chemical Engineering from University of Cambridge. She has been working in the field of non-destructive testing ever since. She is a chartered engineer and she sweep parts level 3. Her main expertise in non-destructive testing is ultrasonics, including both conventional and advanced techniques. Advanced techniques include laser ultrasonics, phase array ultrasonic, high precision ultrasonic inspection, and so on. The type of projects he has worked on include research and development of advanced inspection techniques, design and verification of inspection configuration for complex geometries, software developments for inspection prototypes, performing on-site and in-house inspection. Those cover a wide range of industries, including oil and gas, nuclear, aerospace, energy, and transportation. Ladies and gentlemen, could I make a request? Could you off your mics, please? Otherwise, there will be interference at the backs. Request all participants to switch off the mics, please. Thank you. Okay. Our moderator of the webinar today is Mr. Jonathan Wilson. That is his photo. So, Mr. Jonathan Wilson joined TWI in June 2012 as Principal Project Leader in Project Management. So, at the beginning, when he was with TWI, he started the Central Project Management Team and grew this section to a section of 4 project managers engaged in predominantly high-risk projects. His experience of leading projects at TWI is of high-value projects of up to 3 million in value and program with an annual value of more than £2 million. Yeah? All right, so project that he has involved before were from various sectors and are typically cross-functional in nature. And currently, he continues to manage project while also leading the business risk groups. Mr. Jonathan Wilson graduated in metallurgy and material science from Imperial College in 1985. Prior to joining TWI, his first job was in the metallurgy labs at the Royal Small Arm Factory in Anfield. He later became the section manager of metallurgy departments. And following that, he moved to Ciba Composites and works in quality assurance for 3 years. And later, he became the chief production manager for a further 4 years. And then he moved to a high-tech optical media research and manufacturing business. Initially as manufacturing engineer, then process development team manager. Following that, he spent 7 years as a global product manager and regional sales manager in the optical media and photovoltaic market. Principal product were precious metals, sputtering targets generating annual revenue of more than $6 million. Ladies and gentlemen, those are the background of our speaker and our moderators. And I would like to inform you about the procedures of raising question and answer here in this webinar. So you can always put your message online through the MS Teams meeting chats, or you can also ask your question when it is invited by the speaker. And we have at the end of the presentation open to question and answer. Ladies and gentlemen, to proceed on, now I would like to pass over the mics to the moderator, Mr. Jonathan Wilson. Over to you, Mr. Jonathan Wilson. Thank you very much.
Good morning and thank you. I'll just share my screen now.
It's on the screen now, Jonathan.
It is on the screen, yes?
Yes.
Okay, thank you. Okay, thank you for that. Thank you very much for the introduction. Hello and welcome to today's webinar. Thank you for taking the time to join us today. Today I'll be giving an introduction to TWI and the MAGIC project. This will be followed by a more technical presentation by my colleague Lu. At the end of each presentation section there will be a break for questions. Please do make use of the chat function if you prefer to ask questions in that way. Thank you. TWI at a glance. TWI is a membership-based company and we've been around for about 70 years now. Our members range from small local companies to multinationals. We provide technical services to our members, consultancy on materials, corrosion, failure investigations, NDT techniques development and training, and certification of personnel, welders, inspectors and welding engineers. We take ideas and drive innovation through to tangible benefits for our members, and the MAGIC project is a good example of that. On site at TWI in Cambridge, we also have the National Structural Integrity Research Centre, and we have a number of postgraduates doing MScs and PhDs in related research into structural integrity and so on. What is it that we help our members achieve? Well, our mission statement reads that we exist to provide authoritative and impartial expert advice, know-how and safety assurance through engineering materials and joining technologies. What does this mean in practice? Members come to us with technical challenges and we help our members to effectively apply joining and allied process technologies, demonstrate product safety, integrity and performance, establish causes of failure and build a case of continued operation should we need to. We help companies to join materials, assure the quality of the joins, maintain the integrity of these products and assets through their life, and should they fail, we also help them to understand why that happened. What sectors do we serve? TWI covers a broad range of sectors: aerospace, space exploration, automotive, rail, marine, hydroelectric, offshore oil and gas, nuclear power, wind turbines, heavy construction equipment, the construction industry itself, welders, training and certification, microelectronics, joining, automation and automated or robotic welding processes. At what stages do we support our customers? Indeed our industrial members, basically at every stage. Beginning with design. We help our members answer the questions: what is the best material to use in terms of service input? What is the best material to use in terms of in-service performance? How will the joining process impact the performance and life of that material? Should you coat it to improve its performance? How do you assess the join during manufacture and in service? We help answer these questions through a combination of material science, metallurgical knowledge, and we have experts in steels, corrosion resistant alloys, light alloys, composite materials, polymers, ceramics. And we are able to assess materials and joining products and coatings through standard or bespoke testing, whether that's tensile, fracture, fatigue, corrosion, aggressive sour environments, or a combination of all of these. Additionally, we also predict product performance through numerical modelling and simulation, so you can design and operate better, safer products. Especially relevant to today's webinar, TWI's extensive knowledge and expertise in non-destructive testing and inspection techniques. We have great knowledge in technologies that solve problems. Our members come to us with challenges. TWI has experience and experts in many joining and inspection technologies. We can pull from the spectrum of joining processes: arc welding, electron beam welding, friction stir welding, laser beam welding, diffusion bonding, adhesive bonding. And from inspection techniques, we have great knowledge of radiography, ultrasonic inspection, phased array ultrasonic inspection, dye penetrant, magnetic floor inspection, acoustic emission, eddy count. So this allows us to assess different options to joining and inspection problems and identify the optimum solutions. We also assist our members through the production and operation phases of their assets. TWI can help you to understand the impact of welding and joining and processes on materials, properties and structural performance. We can assist you plan and optimise construction and maintenance. We also provide structural integrity and degradation assessment of structures and assets. And through testing and simulation, we are able to establish the relationship between materials processing, microstructure and properties and share that understanding with our clients. In summary, we are able to provide assurance to asset owners through the life cycle of their products. At the end of the product life, or if there should be a failure, we are able also to support our members with failure investigations. We can support our lead failure investigations to establish engineering root causes. We can develop and implement the case for continued operation and repair through testing and evaluation. We also provide technical expertise, expert witness to solve disputes and support litigation. TWI is able to support our members at every stage, from technical inquiry through to contract R&D consultancy work. Core research programs also provide basic blue sky research on related technologies. We also have many publicly funded initiatives to support our core research program and also innovation. We also provide supplied, certified and also bespoke training programs along with professional membership. Our integrated approach and ongoing leading development work allows us to provide a complete package to support our members' needs. TWI has great knowledge of non-destructive testing, and it is this in particular that's relevant today. TWI provides innovative solutions to inspection problems. We develop techniques and procedures, and we understand not only the techniques but the underpinning theory that allows us to assure the chosen inspection approach. We use statistics and reliability, determining and using detection and sizing data to support the validation and qualification of NDT techniques. We also use software and modelling and application validation to review and assure the quality of chosen inspection techniques. We're also able to provide qualification to ENIQ or other codes. We can support third-party audits and assessments, or provide third-party audits and assessments, and also provide on-site inspection services. Looking a little bit more detail at the MAGIC project itself, TWI was engaged to support UniKL to develop advanced NDT capability at MIMET. We provided this competence through training and certification and developed a technology, the MAGIC vehicle and topside unit, and provided this to MIMET through a technology transfer program where we came across to Malaysia and installed and established the technology at the site. We provide support to UniKL to industrialise the technology, establish an NDT technology and commercial services centre at UniKL's coastal MIMET facility in Limont. The project itself is broken down into 4 different work packages. The first work package was aimed at students with graduate and postgraduate qualifications, and we provided appreciation of basic NDT training, CSWIP visual welder inspection, train the trainer welding programs, CSWIP level 2 NDT courses, dye penetrant inspection, magnetic particle and UT and phased array training. Work package 2 was the development of the phased array ultrasonic inspection technique to inspect a ship's hull and through a marinized crawler vehicle that crawls along the ship's hull to inspect the welds. Work package 3, TWI visited MIMET to deliver the vehicle and the system and train staff how to operate the vehicle, gather data and generate reports. Work package 4 is deployment procedures for the vehicle and also a demonstration in the shipyard. We went to a shipyard in Port Klang, and when we deployed the system onto a ship in seawater, which was challenging due to the nature of the the water was quite dirty and the current was very strong where the ship was moored. Along with that, we've also provided support to UniKL to commercialise the MAGIC system, along with using analysis software such as RiskWise. Okay, thank you. So that's a brief introduction to TWI and a brief introduction to the MAGIC project. After each topic, when Lu goes through her presentation, there'll be a break and we can answer questions at that moment. If anybody has any questions now, I'd be happy to answer them. Okay. Lu, if I'd like to hand over to you now to take us through the more detailed technical presentation.
Thank you. Let me share my presentation. Right, able to see my presentation?
Yes.
Yes, on the screen now.
Oh. Well, thank you very much. And good morning and good afternoon to all. Thank you very much, Professor Kamil and John, for the kind introduction. It is my pleasure to have this opportunity to share the work we have done on developing this MAGIC pilot systems. And so in my presentation, I will answer some basic questions like what MAGIC is, what it does, and what it is comprised of. So as introduced before, the core of the MAGIC is to perform underwater inspection of the ship hull. And to achieve this, it needs to have a few basic functionalities. The picture image on the top right is just a large-scale illustration of how it could be potentially fit on the side of the ship. So the requirement is that it needs to be able to navigate on the ship hull via remote control, and it needs to be able to inspect the ship hull with a thickness range of 8 to 20 millimeters. It needs to go under the water to do the inspection up to 20 meters. It needs to be able to find where the weld is and follow the weld during the inspection. It needs to provide full volumetric inspection using the advanced systems we developed. I just want to mention this point because at the moment, inspections are done by the diver using a touch and feel. So most of the time you observe what's happening on the surface, but really what's happening or what might be present inside the weld that is not visible is unknown at the moment. And also during the inspection, you want to have an overview of where the vehicle is on the side of the ship, because once it disappears under that waterline, you don't always have the visibility. And in the end, when all the data are gathered, you'll be able to have some analysis capabilities that is offline that allows you to review the inspection you have carried out. So if I just summarize that image into a key component sketch. So everything, the hub of the MAGIC system is the topside unit. It takes the mains power supply and subsequently applies power to and receive information from the subcomponents that include the vehicle itself and the two hydrophones. And I would like to mention that the vehicle can adhere itself onto the side of the ship, but we always use the tether as a safety precaution and in emergency rescue just in case. So what does MAGIC consist of? MAGIC consist of? It has three main subcomponents. One is the vehicle, which is the body that carries other subsystems. The other one is the ultrasonic systems that is key and a core to the inspection technique we developed. And then the location systems, which allows us to know where the vehicle is on the side of the ship. So I'm going to go through them one by one. The first one is the underwater vehicle. If I break the vehicle function into more details, it needs to be able to do the following. It needs to self-adhere to the hull. It's able to move and turn on the side of the ship. It needs to have communication with the surface. It needs to be able to carry the systems to track the weld and to perform the inspection. It needs to feed back to the top side surface where I am. And also there's basic mechanical electrical controls. The functionality we haven't included in this version is the surface cleaning, which could be something for the potential next generation or next generation product. And here is how the vehicle looks in the design and in reality. To achieve its required functionalities, the casing of the vehicle is marine-grade aluminum and is fully marinized up to 2 bar, corresponding to 20-meter depth underwater. And is fitted with 4 lifting eyes, each with 250 kilograms pull force, so that the vehicle can be transported and tethered and rescued. And behind the vehicle, there's a 50-meter umbilical cord, so the vehicle can navigate on the side of the ship, while the topside unit is on the surface. And it's installed with permanent magnets for adhesion. It carries the lasers, the cameras, the phase array probes and encoders. And also the control is done by a joystick with a very simple graphical user interface. I'm going to go through this functionalities in a little bit more details, pointing out this design. So the picture on the left is the back side of the topside unit, many cables, and it supplies powers to the vehicle. And there's also data communication lines to send commands to the vehicle. And there's also a video feedback, so we can have a live view from the camera that's carried by the vehicle. And to achieve the movement and steering, 2 inertant tracks are attached on the vehicle chassis. We can achieve independent motions per track, and with maximum speed being configurable. So by controlling 2 tracks independently, we can move it not only forward and backward, but also perform turnings. This is the simple joystick control, similar as the one we used in gaming. So quite straightforward. The left button go forward and backward to control the left track. The right button move the forward and backward to control the right track. And the adhesion is done using the strong permanent magnet banks. It's installed on either side next to the tracks. The height is adjustable depending on what is the hull thickness we're going to inspect, because you want the magnet to be strong so it doesn't fall off, but you don't want it to be too strong that you're using a lot of the motor force to compensate for the friction. So we allowed it to be adjustable depending on the ship hull thickness. The thicker the ship hull, the stronger the magnetic attraction, so the higher we can lift up the magnet. And this is the control software, again quite straightforward. And besides controlling, what we have is we allow the monitoring of the temperature and relative humidity inside the vehicle as the sensors we can introduce. Although this vehicle is fully marinized and waterproof and tight, but just in case if there's a leak, we were hoping to identify the leak before it causes short circuits into electric components. So the relative humidity is a way of monitoring whether there's water inside that's evaporated and leading to the increased humidity. But so far we haven't had such an incident. So we don't know what is the humidity reading if that happens. But this whole temperature and relative humidities are being locked right from the beginning. The latest number is displayed, but you can see the plot showing that the historical temperature and relative humidity since the operation of the system. And the speed underneath, it just simply show the speed of the left track and the right track. So that's how the vehicle works. And the core part is the inspection. And the inspection is not just only sending ultrasound signals, but also knowing that you have positioned the probes at the right location. And we have 2 ways of tracking the probe. The first one is the vision system. It's camera and laser based. That's like our eyes directly into the as for the vehicle. The camera is a self-illuminating waterproof camera, and the laser is a normal fan-shaped diode laser. And this is just a presentation to see. The laser projects the beam, and is projected as a line on the side of the ship hull or the sample, and that line is adjusted to be right in the middle of the vehicle. So that's the center line of the vehicle, and more importantly is the center line of the probe, so of the inspection configuration. And the camera, once illuminated, it's able to observe the sample, meaning we can see the weld cap as well as the laser line. So to make sure if the vehicle is traveling a bit off track, we're able to adjust it so that the center, the green line, falls right parallel to on top of the weld cap. And this is a video showing how it looks when the camera is taking the video. So you can see the green line. This is the video of it coming out of the water. So you can see the reflection of the light, and at the same time you can see the green laser. This tick is because it's going in and out of the water. So the other side of the laser is just being reflected. And this video was taken in the small immersion tank in TWI. And this is how it looks in the test demonstrator tank in UniKL MIMET. So you can see this is actual weld cap here, a little bit more rusted. And this is the green laser light that's just projected. And there are more dust particles and dirt in the water, but the camera in this kind of clarity is able to see through the dust particle, the rust particles in the water, and observe and record the vehicle moving forward along the weld. So, yeah, and so this is our eye on the vehicle using this camera and laser-based systems. Then, well, I'm going to talk about our phase array system, which is the advanced inspection part of the whole system. To design, this is a bespoke inspection system, so not out-of-the-shelf commercial products. We used the OEM hardwares and designed 3 probes, which are later customized. They contain 128 elements in total, and out of these 3 probes, 2 were used for weld inspection using sectorial scans. They are placed on either side of the weld, and the one sitting right on top of the weld is a phase array probe, which we used as a weld follower. And this system, the inspection, in order to know and size the flaw, we also fitted it with encoder systems, which is not forward calculation based on the motor control, but it's just measuring how much the vehicle has traveled on the surface. So that's independent from the track motors, and we acquire the data at 1 mm resolution. One more thing I want to say is that because this is designed for different ship hull thickness, so the standoff of these 2 probes needs to change according to the thickness. So we have designed the slots to change the probe standoff relative to each other, and I will show what it means. So to develop the inspection technique, we perform the scan plans simulation as well as the flow response simulations. 2 for the sectorial scans and 1 for weld following. So I'm going to go through quickly how the scan plan was developed to make sure the full weld is covered with our developed technique. And we perform subsequently simulation to ensure that the weld volume and the flaws inside can be covered. And we did a scan plan using the for the linear probe, just to test out its capability in testing in tracking the weld. So, and this is the simulated results of tracking the weld. So the principle is that this is a 0-degree probe shooting down the beams, and one is hitting the top side of the ship hull. It produced nearly straight 0-degree returned beam, and is projected to be flat. However, on top of the weld cap firstly is slightly higher than the rest of the ship hull surface, and at the same time it diffused ultrasound, so the energy intensity is slightly weaker, and it produces a wider spread of the beam coming back. So using this principle, we'll try to track the weld cap to make sure it always lies in the center of the weld follower probe. And this is one example. So this screen is the screen that the operator sees live during the inspection. So these two displays are all pertaining to the weld follower. So on the top, what you can see is that we use the second top surface frontward reflection here. So this is where the ship hull surface is, and this is where the weld cap is. The idea is to try to position the weld cap close to zero. We're now about 8 millimeters off. And here is just the track of the historical path of so this zero is where we're aiming to position the scan of the weld cap image. And so now the operator sees this image and now needs to adjust it a little bit so the vehicle moves further towards the left. And this is the offline data analysis. So this analysis will not only show you the C scan and the B scan you see earlier live, but also the sectorial images acquired using from the weld inspection probes. So I just want to go through this again, introducing a bit of functionalities. You can adjust the gains, and the cursor you see here is adjustable from the beginning of the inspection, which is 0, to the end of the inspection. In this case, the test is 200 millimeters. And while you move this cursor, these 3 scans below will change to what the B scan and sectorial scans were at this particular location. So this just shows at this particular location, the weld is nearly in the center, which is consistent to what we see here. And these are what's inside the weld volume. I'll talk a bit about this before. On a test plate, this signal is reflecting one of the artificial flaws we introduced. And then from each of the B scans and sectorial scan, the subsequent cursors, which will allow you to see the A scan exactly at that position. So here you can see this signal representing the weld cap, and in the next image you'll see when we move the sectorial scan cursor, you're able to track which angle you're reading and what is the A scan corresponding to that particular angle. So that is the inspection system and its functionalities. And besides inspection, another thing we said about before is once the vehicle disappears onto the waterline, we would like to know where it is globally, not just whether how well it is traveling over the cap, but also on the ship hull where it is. I mean, there are other clues, like you can observe where the umbilical cord is going down to see maybe roughly where it is, but we need to keep track and record its locations. And to achieve this, we used a sonar-based location system. It tells us where it is the vehicle is on the ship hull, and also tells us in which direction it is going at the moment. So this is like another graphic illustration of how we design the systems. So we use 2 hydrophones as receivers positioned on either side of the vehicle on the ship hull. And the vehicle itself, it carries a pulsing sonar that sends pulses at 1 second interval. And these hydrophones are tuned to receive the particular frequency sent out by the sonar. And the vehicle also carries an inclinometer, which tells you the posture of the vehicle, in which direction it is traveling. And this inclinometer is chosen instead of a gyroid because it's not affected by the strong magnetic field that's produced by the permanent magnets. It also carries a pressure sensor, which will allow you to know at which depth this vehicle is underwater. And so given these information, we can do a simple calculation to work out where the vehicle is with respect to the depth, and also on the side of the ship hull as marked by the hydrophones. And this is the sample interface that the operator will see live during the inspection. So the plot underneath, for the plot underneath, the 2 green dots shows where the operator have deployed the hydrophone, and here it shows the depth of the hydrophone. And the blue dots just marks the path of the vehicle while it was traveling on the side of the ship hull. And the red circle just highlights which is the current position of the vehicle. And you can also read off the current position from the box over here, but this is just a more visual display. And this dial here shows the inclination of the vehicle. So when the needle is pointed up at 180, that means this vehicle at this moment is facing straight up. And when it's going down, you'll see the needle pointing at 0 because the vehicle is traveling head down. So these are the subsystems we have designed and manufactured and assembled for the vehicle. And what we did after having this vehicle ready is we performed site trials both in the UniKL MIMET and a shipyard. And you can see this is not a simple test we're doing. So to perform the test in the UniKL MIMET, we need to design the test facilities. So we design and manufacture a demonstrator tank. We design and manufacture some test plates. And the UniKL MIMET workshop is well equipped with lifting equipment to enable the deployment of the systems and setting up the demonstrator tanks and plates. So during the test setup, we need to be able to simulate the ship hull. We need to be able to load and manipulate the test plates. We need to be able to load and deploy the vehicle. We need to be able to deploy the hydrophone and have a space to set up the topside control unit. And when these are all ready, we perform the inspection trials and the data analysis report. So I'm just going to talk a little bit about how we did the design and construct the test facility. So this is the demonstrator tank. It was first designed and manufactured in the UK, and subsequently it was shipped and assembled in the UniKL MIMET site. They fitted the staircase for access. And these tanks are internal dimensions are 2 meters long, 2 meters wide, and 3 meters deep. It's fitted with water inlet and outlet valves, so that we can fill and drain the tank. And the last picture is how it looks when we have fitted the topside unit and other accessories in the test facilities. And these are test plates we designed. We sourced plates of 2 different thicknesses, 8mm and 10mm. And for each plate, we introduced, they were welded together. So each plate has got 3 welds. And the artificial flaws are introduced in these welds. And more importantly, these plates, we also design and manufacture a jig. So these plates can be deployed in various orientations, simulating the side of the ship hull. So here is just, I'm going to go through how it looks in the design. So there's a test rig where they can lift the plate and also can hold the vehicle onto the plate. So we lower the whole thing into the tank, and we're able to pull the strings to change the orientation of the plate. So it goes from flat and slanted into vertical, and it can also move upside down to simulating the worst case scenario. The bottom of the ship is flat and upside down, and we need to make sure the vehicle is still be able to adhere to the plates and travel on the plate. So this is the test rig, and this is just some pictures showing that us doing the test there. So we lift and deploy the test plate on the rig. It's lifted by the overhead crane and lowered into the tank. And the one is in the tank in the vertical orientation. I just want to show you this is how we fitted the hydrophone. And if you look on the right side, this is how the hydrophone looks. It's deployed by a magnetic trolley, so it can also be adhere itself to the ship hull, and we can push it up and down because it's these magnetic wheels. And this is just a picture of the vehicle when it's traveling on the side of the plate, when the plate is in a vertical position. This is clear water, it's quite close to the surface, so we're able to see the vehicle, the laser, and the camera. This is during the live inspection. You may find this screen a bit familiar. So this is the live screen the inspector will see. And by looking at the screen without looking at the vehicle, we'll be able to drive the vehicle on the plate, following the weld. So this is the camera view. You might just be able to see the green light right on top of the weld cap over here. But at the same time, you use the B scan and C scan to make sure that you're traveling right along the weld. And after successful tests in the demonstrator tank in UniKL MIMET, we also brought this system to a shipyard for testing. So this is an actual ship where we deployed the vehicle on the side of the ship hull traveling down, and you can see here is the tethering system we have for the safety for the safety, and this is the umbilical cord that is trailing behind the vehicle, and because of the space constraint, we deployed our sonar hydrophones on the side of the dockyard, as you can see over here. I'm not going to share the data we collected on the ship, but this is just example I've used before. So this is how the data will look like while it is traveling on the ship, and you can choose different slices to check for whether your vehicle is on the right position and whether in your inspection probe you observed any signals that you need to report. So that's all I have on the vehicle itself. I will just quickly check if there's any questions on the chat. If there's no question, I will.
Maybe you open up the meeting chat. Could you open up the meeting chat? There were quite a number of questions being raised through there.
Okay. Okay. So let me just go through this. So the first one. Feel free to drop in that. How reliable is this underwater vehicle? Is there any incidences of the underwater vehicle fall off? Right. So this is the design iteration. In the beginning, in the design phase, we got cases that maybe the magnets are not in the right position, not strong enough. But after the iterations, the underwater vehicle became quite reliable. We tested with the lower spectrum of the design, which is 8mm thick plate, and that's the case where it's more prone to fall off, and we don't have incidents of it falling off in the end, and it passed the test and with the witnesses, etc. The second question is, can this vehicle go against water slam? What are the protection or rectifying positions from the wall if it falls off from the wall? Water slam, does it mean strong current? Or, right. So I'm going to assume it means the water splash and strong currents. And we have tested this as well, especially when we go to the shipyard, because the magnetic force attraction can be calculated against the vehicle load, against the vehicle weight and the load. So it didn't fall off, it's quite stable. The protection mainly is from the tether. There are two kinds of tether we can use. One is the fall arrest. So the moment it senses the vehicle doing a free fall, it will just capture it. So there's not a swing, so they won't go any further. And the second tether you see here is just to make sure if it falls off, it doesn't do a free swing. So it's locked where it fell off without swinging into the vehicle. And subsequently, we can use that as the pulling strain for the rescue. I hope I answered the questions. If not, feel free to bring it back again in the chat box. The next question is, while the inspection done by the underwater vehicle probe, had it been approved by classification societies? Okay, this is a very good question, because at the moment, there are standards governing the phased array inspections, and I think there are standards governing whether a ship is allowed to sail. But at the moment, there's no requirement to perform volumetric inspections of the weld. The current standard only tells you how to use diver to do touch and feel inspections underwater. So that's why we're doing something new and innovative here. So it is not part of the standard work, but it's the work that we felt is necessary and maybe in future can make it into the standard. So it's not, so we can't say it's approved by classification societies because we're still being in the innovative stage here. The next question is, what is the typical setup of equipment on board the ship or FPSO? Any limitation and restrictions? I'm not sure I quite understand. So the limit is really you need to be able to put the topside unit, and you're allowed to drive the vehicle down the side of the ship, and the distance has to be within our. Sorry, if I can just kindly ask participants to mute the mic. So you need to be able to so the coverage has to be within the range limit designed by the vehicle, so which is 20 meter depth maximum, and the umbilical cord, which is 50 meters. You can't, so from where you deploy the topside unit, it can't travel for more than 50 meters from there. That will be the limitations. So the next question, just wondering how strong are the magnets? We have experience using a robot for the inspection of the jacket structures, and the magnets were not reliable. Any experience on robot falling off? Yes, so we came across these issues in the beginning of our design as well. So there are ways to calculate and model the traction you can potentially have. And here we used permanent magnetic banks. There are other alternatives where you can use magnetic wheels. So basically you need to consider the thickness of your the material and the thickness of your target, and what is the load and the weight your vehicle is carrying, and also your speed and what's the requirement you need to do turning or just traveling forward and backward. So there are ways to do the estimates and eventually to have it tested. Experience robot falling off in the beginning, I have to say we didn't have it, but through the iteration of designs, it gets better. Is the topside unit EX certified? So Judy, did you mean export certified?
I think they mean flameproof. So is it? I would imagine it's as in non-sparking. So.
Right. No, we didn't take that into the consideration in the design. No, it's an industrial, it's a robust unit, but we didn't think of explosion. I think you might be talking about some sort of ATEC certification, yeah, where the voltage is not allowed to go above a certain level. So no, we didn't. This one takes the mains power supply, so I think it's 220 volts. So unfortunately, it's not explosion certified, explosion proof. Okay, so that's all the questions I've got so far. Feel free to drop in more, and we'll just probably open the session to the whole floor after my last presentation, which I'm going to talk about fitness for service. Stop sharing options. Stop sharing options. Share content. Right. So am I back into my sharing screen now?
Yeah.
Okay.
Yeah, that's
thank you.
fine.
So what I've talked about so far is the systems we designed to collect data and to provide, to travel on the ship side to collect the data and to analyze the data. Because this is the innovation project, what we're asked to provide as one step further is, so now you know what are possibly indications in the ship hull, which in current standard none is allowed. But if some indication is found, then what do we do? And as mentioned before, this is not part of a standard yet. So what we have in our arsenal, is that the right word, is some way of assessing whether an indication or a flaw that we sized is tolerable. We call it's the CrackWise software we official itself, but that is based again on the international standard. So I want to start this discussion just from a higher level up, from these concepts of fitness for service, FFP, and the lifetime assessment. So with general inspection, not just for this one, what we frequently got asked is that, okay, we did inspections and these are the flaws we found. Unfortunately, the standard will say these flaws may not be tolerated, or we're not sure that in this our particular scenario, which is not strictly using the acceptance criteria from the standard, because we may be operating on the more sensitive case. This is long time in service. What are we going to do next? We found these indications. Is this structure going to fail? And if this structure is not going to fail, how much longer can it last? So this is the general idea of the assessment we carry out after obtaining inspection data. So it assesses the crack-like flaws for the implications on the fracture and fatigue. That's the official line. So there are two failure modes we're talking about here. One is the fracture failure mode, which is more like imminent failures. So when we assess whether this particular condition will undergo fracture failure, we are assessing its fitness for purpose. And that's a simple yes, you can use it or you can't use it. And another failure mode is called fatigue failure mode. And that's when we say, in the current operating condition, with the flaws you find, it's not going to fail imminently, but we can tell you how much longer it can last before it fails. So that's assessing the remaining lifetime. And there are two existing international standards governing this kind of assessment. One is called BS 7910. This particular standard is applicable for all the crack-like flaws in metallic structures. And there's another standard, API, American Petroleum Institute Standard 579, and that's applicable for all the other flaw types, like the general metal loss, local thinning, dense pitting, etc. But it doesn't cover extensively on the crack-like flaws. So these two standards complement each other quite well. But in reality, the most dangerous flaws, or the flaws that has potential to grow very quickly, are the crack-like flaws. So what we focus on here is using BS 7910 as the guide for assessing our situation. And I want to talk a little bit more about BS 7910. If I'm to use one sentence to summarize BS 7910, it's a guide to methods for assessing the acceptability of flaws in metallic structures. And this is so it offers an alternative approach for assessing the suitability or acceptability against the tolerance levels in the fabrication codes. And this was first developed in the 1980s under different names, and it gone through several iterations through history. And the latest version was released in 2019. And so that's the standard. And CrackWise is the software developed by TWI that automates this calculation, because BS 7910 is a thick guide full of formulas. And you need to go to the right formula based on the assumptions you make and the scenarios you have. And CrackWise just provides a tool to automate and make it easier for the users to utilize the standards in order to calculate and the fracture and fatigue assessments. We are developing we're developing the automation of the software, and also because TWI, we are the leading committee that publish these particular standards, and our member of staff is the chair of the BS 7910 committee. So we're in a good position to understand the applications and limitations of the standard, and hence in a good position to automate it. So that's why although this is a published standard internationally used, but we are in a good position to produce a software to automate its application. And this standard is widely used in different industries. It started from oil and gas. It's very widely used in oil and gas, but it's also applicable to all the other standards. And so far, we have sold more than 200 licenses with customers, including Shell, BP, Technics, and so on. So as I said before, so these applications, besides oil and gas, it can be it can be storage tanks, pressurized vessels, turbine blades, buildings, bridge and castings, and potentially also ship hulls. And this is just an example interface of the Crackwell software. It's a Windows-based where you can click through each stage and leading to the end results of your analysis. A little bit on the details of what's inside the BS7I10. So it produced basically two types of assessment, fracture and fatigue. And in the fracture, I said before, they produce a FAD, failure analysis diagram, which allow you to assess whether the flaw you have is within the curve that's acceptable or outside the curve and is not acceptable. And with the fatigue, it gives you a plot where you can assess how fast or slow your flaws are growing. And to come up with this type of analysis, there are three factors, three inputs that is related to each other. One is the geometry of the structure. The other is the stresses, be it static load stresses or the cyclic load stresses. And then also material properties. So what materials you're using to build the structure. And I'm going to cover some important critical features of this software and of the BS7I10 to show you what type of information you can get out of the assessment. So I will go through these plots in a little bit more details, but basically what it tells you, so first of all, the fracture assessment procedures, including Terrell single point toughness. So it tells you whether the flaw you have will lead to failure or not failure. And second of all, what is the critical flaw size that is on the boundary of the failure analysis diagram. So, so the critical flaw size means anything below you will not fail, anything above you will fail. And also you can calculate how sensitive the structure is to your flaw parameters. So when you vary the length and the depth of the flaw, how fast or how slow you're approaching that borderline of the failure analysis diagram. So the second feature I want to mention about Crackwise is that you can address different geometries and a wide range of flaws, be it plate or pipe, or nozzle or sphere or bar, and the flaws you can calculate because they will all have different impact on your structural integrity, and also they will have different growth rate. You can be surface flaws, through thickness flaws, edge flaws, longitudinal along the surface, embedded flaws, or the corner flaws. And these are some additional toolkits for you to input and calculate the material properties. So I'm going to go through a little bit more details of what is the output, like the diagram I showed before. So in this failure analysis diagram, you input your flaw size, you do a computation, and it will tell you that this is the point you end up on the failure analysis. And this is where you say, okay, so this is safe, this is acceptable. And if you input your flaw dimensions and the point the software computed for you, and somewhere here in the KR and LR, that means not suitable, not fit for purpose. So this is the most basic and the first calculation you will do. And here you will vary your flaw dimensions and to see at which flaw dimensions the calculation, the output of the calculation will end up right on this failure curve. And that is your critical parameters. And you know that's the uppermost of a tolerable flaw size you can have. And if you start from your existing flaw size and you change, so for example, you change the A, which I think is the thickness, the through-wall height of your flaw, and you gradually increase the through-wall thickness, and you compute the outcome. And So you end up with a series of a point. Like in this case, your thickness changes from 5 to 25, and you know between 5 to 25, you're all still within the failure diagram acceptable range. So this is the sensitivity you are to this flow growth. So this is the sensitivity parameter analysis. And this one is the critical sensitivity parameter analysis, which, so this is not a KR and LR, is where you have worked out the tolerable flow size along your failure diagram curve, and you plot their length with their height. So this is the critical flow size combination. So that just means if your flow is really short, then you can tolerate it to be higher in through wall dimension. But if your flow is long, then you have a shorter tolerance on the through wall height. This part is a bit of common sense, but it tells you exactly where you start to level off. That means this would be your cutoff through wall height. Anything smaller than this is more likely to be safe for a very long length of the indication. And that was for the fracture analysis. This is for the fatigue analysis, where you can use your life cycle. So when we talk about remaining lifetime, it's not really, in a calculation, it's not in terms of days and years directly. It's in terms of how many stress cycles the structures undergo. Then you can apply that within a given duration of the time, how many stress cycles you will undergo. Sorry, is that a question or?
Could you please mute your microphone?
Yeah, sorry about that. And you can work out what's your crack growth rate until you reach the fracture point as assessed by your fracture failure diagram, failure analysis diagram. So that's all I want to cover on the assessment. And we're hoping to marry this assessment with inspection data we get from the Shipyard in order to provide better information on the overall management of the structure. So that's all. Any questions? Let me check the chat box.
Is there any more?
I don't see more.
Mm-hmm.
Okay.
So we can open up to the participants if they have any more questions.
Yes. If there's no more question for now, Professor Kamil, I'll pass the presentation back to you.
All right. Okay. Thank you very much. It's been very informative presentation by Mr. Lu. And if there are any further questions from the participant, you can always forward it to me as a facilitator. Probably I can forward to Mr. Lu later on in TWI UK. All right. So with that, we'll go for the next agenda. That will be a short video presentation about the major equipments. I will share with you in a minute, ladies and gentlemen. All right, ladies and gentlemen, can you see on the screen now? Okay.
Not at the moment.
Not at the moment?
No.
Let me do it again. What about now? Can you see anything on the screen? Nothing? Oh, no. 1 minute. What about now? Can you see, ladies and gentlemen?
No, nothing at the moment.
Nothing?
No, we're still seeing the video, the just normal pictures of themselves.
Sorry, I don't know what's going on. Tak ada apa yang ada kat sini. Terus Can you see now, Jonathan?
Just the file explorer screen, not video.
No, 1 minute again, sorry. Saya tak masuk.
Saya ada bagi link kat dia, saya cuba play daripada sana directly.
Okay, try ya. Okay. Angkut. Okay, my technical lesson will get it connected in a minute. Sorry about it.
Dekat Facebook keluar.
Yeah. Sorry, we were checking on the Facebook. On the Facebook is okay, no problem. But on here, it's like problem. Yeah. 1 minute. Sharing dah pula. Ini tau, ini kat sini tau. Di sini.
That's it. We can see the video now. Yes.
Can you see now?
Yes, we can see that. Yes.
Can we just break for 1 minute? Because there's a
So while you're adjusting, John, I think I saw a question come in on
Sure.
what's the approximate size of the vehicle?
All right, Mrs. Lu, you have some question to be answered there, is it?
Yes, so while you are
Sorry.
it, I think I can go on with the Q&A.
Sure, no problem.
Yeah.
All right.
Right. So the size of the vehicle, that's a very good question. John, would you say
It's
400?
it's about 400 millimeters long,
Yeah.
by about 300 millimeters wide by 300 millimeters high.
Yeah.
Overall, the vehicle weighs, I think the total weight is about 37 kilos.
Yeah.
So it uses the magnetic clamps to obviously hold that onto the surface and so on. But yes, that's approximately the size of it.
Yeah. Thank you.
Any more question? Any more question, Mrs. Lu, from the message chat?
No, I only saw this one.
All right, so if there is none, I think we proceed on with the next agenda. That will be on background introduction of UniKL Resources Neighborhood. Is one of the consultant partners in this MAGIC projects. That will be presented by Mr. Zamari. Over to you, Mr. Zamari, please.
Professor Kamil, I think you're sharing the screen. You have a loop.
Good afternoon and very good morning, ladies and gentlemen. UniKL Resources Neighborhood, in short URSB, URSB is a wholly owned subsidiary of Unitech Mara to manage UniKL operation on non-academic business, commercial entity in providing cost-effective services to clients. It is our mission to become the leading entrepreneurial technical university by leveraging our industry, professional team, and scholars. URSB Marine, located at UniKL MIMET Lumut, a strategic location, is well equipped with shipyard facilities. URSB UniKL MIMET Smart Partnership provide on-campus teaching factory, give a hands-on industry exposure and experience for our students. The MAGIC equipment is placed here in NDT workshop of UniKL MIMET. It serves as the commercial technical service center for underwater well inspection for a ship. For further inquiries, please contact +605 690 9000. Thank you.
All right, Jonathan, that's about no. All right, Jonathan, that's about all the background of UniKL Resources Neighborhood. So I'll pass it to you for the closest, please, Jonathan.
Okay, if just open the discussion to the floor, really. We've had the introductions to UniKL, to URSB, and to TWI. We've also gone through the technical presentations about the MAGIC vehicle and also about the analysis and of the flaws that one might find during inspection. We've had some questions in the chat. Are there any other questions from the floor regarding the MAGIC project?
For this MAGIC project, obvious is for steel ships. Have you had any plans for fiberglass where you cannot have a magnetic attached to it? And also for pout, is it suitable for checking flaws in FRP.
Right, I can take that one. So you're right. So this is only working with steel and magnetic materials. For fiberglass, you're talking about a different set of challenge. So PAUT application on fiberglass, it's limited success. It mainly depends on the fiberglass layout you have, and what's the thickness you would like to penetrate. I think in ultrasonic in general, there's a limitation there. And in terms of traveling, we have not with fiberglass ship, but with fiberglass wind turbine blade. So there are equipments that can drive along the fiberglass wind turbine blade using vacuum pump suction. That's successful. So the vehicle part is fine. But I think the main challenge you'll be looking at is the ultrasound penetration. Having said that, besides ultrasound, there are other methods to inspect fiberglass. I don't know what flaws you may be having in mind, but there are other full field methods like thermography or chirography that can be potentially used as well.
Okay, thank you.
Yeah, you're welcome.
Okay. Does the things like thickness and so on of the fiberglass affected at all, Lou, or is it?
Yeah, because it's very attenuative, so the penetration would be limited.
The question from the floor, do you have any idea on the thickness of the hulls that you'd be inspecting?
I mean, we'll probably share our emails and contacts, so if there are any follow-up, feel free to contact us via emails.
Okay.
Shall I just type in my email address on the chat box? Or
yeah, that'd be good, yeah.
This innovation is actually very interesting. Let me introduce myself. My name is Nur Ashar. I'm from Bureau Veritas, a classification society. Looking at your presentation, yes, there's a potential on this method because it consists of one is the method of inspection, and the other thing is how you're going to carry it out. I believe this is workable, provided several items that you need to consider more thoroughly. For example, PAUT has been accepted on case-by-case basis based on how you apply it at the shipyard. We have done it before in Malaysia. We have approved it case-by-case basis, where one of the items that we look for is we compare the results of PAUT to RT, for example. And it has been used in quite common to be used in shipyards in Korea. On the other hand, the method that we have been using for underwater is using approved divers, because one of the reasons is because you want to ensure the location that we are inspecting can be verified with the drawings and so on. So what you are doing now, yes, you can confirm the location, but most importantly, during the survey or when you apply this equipment, it can be translated to the actual location verified to the drawings. If that can be confirmed, I think it is workable. This is my opinion, because when we do survey for underwater, for example, we use diver. The surveyor would direct the diver which location he wants to inspect and so on. This can also be done, like I said, maybe the surveyor would be sitting next to the operator, and to ensure the location of the item being inspected can be verified to the drawings. Again, if this can be verified, it is workable. Thank you.
Thanks.
Thanks. Okay, that's good feedback. Thank you.
All right. Is there any more question in the chat box? Is there any more, Mrs. Lu?
No, that's all the questions that are in the chat.
Okay, I think that's about all of our webinar today. If there is no more question, I think it has been quite successful from the presentation that we have heard just now, particularly from Mrs. Lu, explaining all about inspection system that we have. And I would like to thank to all participants participating in this webinar from the United Kingdom and also from Malaysia. And we hope that we will have a similar webinar in future of this kind. And now I think I would like to pass over to Jonathan to make the final closer. Jonathan, is that okay?
Okay, yeah, thank you very much. Just to say to everybody, thank you very much for joining the webinar today. Thank you all for your inputs and attention. And if you do have any follow-up questions, please, you're very welcome to contact myself or Lou at TWI. Our email addresses are in the chat there. And also, I'm sure UniKL will also be very welcoming to any further inquiries you have regarding the technology, or indeed things such as training and certification and so on. Okay, I think in conclusion, then that closes out the webinar. I think thank you very much for your attention today.
Okay, thank you very much, Jonathan and Mrs. Lu from TWI. All right, we hope we see again later on in some other occasion. Thank you very much. Bye-bye.
Thank you.
Yes,
bye-bye.
Est-ce que vous êtes prêts? 3, 2, 1, 0. UniKL, UniKL, go! UniKL, go! La 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 la. City